Recording.
Record.
Shall I start, sir? HOD, sir. Shall I start, sir?
Yes, sir, we can start.
Okay, sir.
Start, okay. Start, madam.
Good morning to everyone. I welcome Honorable Vice Chancellor Colonel Dr. G. Tiruvasagam and our most respected Registrar Dr. M. Jayaprakash sir, and our special welcome our resource person Dr. R. Sivaraman sir, Associate Professor, Department of Mathematics, D.G. Vaishnava College, Arumbakam, Chennai, and our special welcome to Dr. L. Rajendran sir, Professor and Head, Department of Mathematics, AMET University, Chennai. I also welcome Heads and Dean of various departments, my dear faculty members and the students for the guest lecture of the program Application of Mathematics in Engineering. Mathematics being a queen of science, yes, which is applied in various fields of engineering, science and technology. Students learn the techniques of mathematics. Today, this lecture will give a highlight about the few application of mathematics in engineering and science. Before that, I introduce my chief guest, Dr. R. Shivaraman sir. Sir is working associate professor at the D.G. Vaishnava College. Recently, sir, 20 years of experience teaching and learning process. He has been conferred with the National Award of Popularizing Mathematics among MOS in 2006 by Department of Science and Technology, Government of India. Is also conferred with the prestigious Indian National Science Academy Teaching Award for the year 2018. He also received two state government Best Science Book Award in 2007, 2011 and 2012. For his contribution to mathematics, he has won more than 60 prestigious awards so far. He has provided more than 300 lectures conveying the beauty, the importance, and the application of mathematics. He has published more than 80 research papers in mathematics. He is also a member of editorial board more than 10 mathematics journals. He was a member of textbook writing committee, Tamil Nadu School Education Department for preparing and revising mathematics textbook for 11th standard. He was a chairperson of 10th standard mathematics textbook. He writes articles and provides puzzles for famous newspapers like Indian Express, Times of India, the Hindu School Education Edition paper, Tamil Hindu, Dinamalar Patam newspaper. Also, he contributed several articles about mathematics in monthly magazines like Ariviyal Oli, Chennai Report, Arumbu, and continue to contribute more. He is currently editor of the journal Junior Mathematician. It is a quarterly mathematician journal for school students, which is published by AMET. He is also the editor of E-Magazine, Mathematical Fiction, published by the Pi Mathematics Association. For the past 20 years, he teaches more deserving and poor students, and he made life there for better living. In the view of spreading mathematics among everyone, with the help of the students and well-wishers, he had initiated an exclusive charitable trust Pi Mathematics Association, being its founder trustee since 2007. Serving the poor people and the needy students was his motto. Now the session is handed over to Dr. Sivaraman sir. Sir, you can continue, sir. Sir,
Yes, sir.
now you can continue, sir.
Okay. Shall I share the screen?
Yes, sir. I request the participant kindly mute your headphone. Again, I repeat you, all the participants kindly mute your headphone. Thank you.
So is the screen visible? Hello?
Visible, sir.
Yes, sir.
So good morning to everyone. I'm very glad that I'm going to provide this guest lecture today in the topic application of mathematics for engineers. At the outset, I thank everyone at the mathematics department at AMET University, Chennai, for giving me this wonderful opportunity to share what little I know with among young students like you. See, the main purpose of conducting this kind of guest lectures and other lectures were to motivate young people like you. So, in that regard, I request rather, you to listen carefully and get motivated by the concept that were presented. This will make your learning more meaningful when you go to your classes. Okay, so that is the purpose of conducting these lectures. So I request you to listen carefully, and if there are some doubts to you, or if there are some questions to ask me in your point of view or in whatever I have presented, rather you can post those questions at the end of the talk. Okay, so let me begin my presentation. See, the idea of applying mathematics into engineering probably started in ancient times, not new. See, the engineers require mathematics for possibly every bit of thing that they construct. Especially, it started with civil engineering purposes when they built great structures like Egyptian pyramid. The one that is shown here at the left side was Great Pyramid at Giza, Egypt. It was it is known that there are more than 100 such structures, nearly 120 pyramids are existing as of now at Egypt. More than 120 pyramids, definitely. And some are big like this, and some are quite short. But this one is most famous because it is the largest pyramid that was seen among the existing pyramids. It was located at Giza. Now, in almost all the pyramids, including the one that is shown here, you find that Egyptians used heavy-duty mathematics. They used geometry, they used trigonometry, they used all kind of measurements to build the grand structure efficiently, and probably that is why even today this stands as one among the seven wonders of the world, right from those periods. Like it was said that it was constructed nearly 5,000 or 4,500 years ago, so nearly 4,000 years ago from now. So it stands all those times and still remains one of the finest architecture in the world. Now, how could have Egyptians, the ancient Egyptians, accomplished this great feat? They had the idea of mathematics in their construction. And let us see a little bit of that, not much, because the mathematics used in Egyptian pyramid construction itself is a huge one. I'm just highlighting some of the things. First of all, you note that the pyramid that the Egyptian constructed were in the shape of square pyramidal shape, in the sense that the bases were squares. There are pyramids with any desired shape base that you can have. For example, you can have pyramids with triangular base, and that is called triangular pyramid. And you can have a pyramid with hexagonal base and any polygon that you choose, regular polygon that you choose. But the Egyptians constructed pyramid with square base, and this numbers the structure that I showed here were called square pyramidal numbers. As you can see, this is one square, simply one. There is only one dot. This is 1 square plus 2 square. There are 4 dots here. This base is a square joining 4 vertices. This is the top one is the vertex. So all these 4 vertices are joined to the top vertex. So this is 1 square plus 2 square. So this is 5. This is 1 square plus 2 square plus 3 square. There are 9 dots. So this is 3 square, this is 2 square, this is 1 square. In that sense, this is 1 square plus 2 square plus 3 square plus 4 square. Now this kind of thing, so each compartment is a square, and all the squares put together were joined to a common vertex representing 1 square, and they form a square pyramidal shape. I can give few applications of this shape also, but We see Egyptians were very clever in many aspects. In one way, they have chosen to construct most of the pyramids, including the one that is shown here, the Great Pyramid, in the sense that the base of such pyramid, the square one, I told you that the bases of the pyramids that Egyptians constructed were squares. So the base of the pyramid that they constructed is such that its perimeter is equal to the circumference of the circle, which is circumscribing the square. In other way, um, they constructed a circle such that the base of the perimeter of the base of the pyramid that they want to construct will be equal to the circumference of the circle. So you know the circumference of circle is 2 times pi times the radius r, where r is the radius of the circle. Now, with this measurement, if you just see radius of circle is perimeter of circle is 2 pi r, 2 pi times radius, and that comes to the circumference formula. Taking pi to be approximately 3.14, pi is not exactly 3.14, but approximately 3.14, and they constructed the radius of the circle to be exactly equal to the height of the pyramid. So they have chosen the radius of the circle encompassing this height of the pyramid. They have chosen height to be 481 feet, and therefore if you substitute that here, you find this answer. This is the circumference. This is the perimeter, and you know that this is equal to the perimeter of the square according to their construction. And perimeter of square is 4 times a when a is side of the square. So this is 4 times a. Therefore, if you divide this by 4, you get 755 feet. And therefore, they have constructed this Giza pyramid by choosing a square base with side of 755 feet and height of 481 feet. So they require geometric construction using a square and a circle to make this structure. This is quite interesting because the value of pi is not known clearly at those times. Nearly 4,000 years back we are talking about, and moreover, what kind of geometric structures that they used is quite amazing, because the problem that they used were purely geometrical, and using this geometrical constructions they could have done it very efficiently. So this is probably the first connection between engineering and mathematics put into practical use very efficiently. Okay. Now, if you look at the substructures that is inside the pyramid, you find so many triangles like this whose ratio whose sides are in the ratio 1:5, where 5 is the golden ratio. So I'm not going to brief much about it now, but you can look at this later. And if you go to any internet source and if you look at all this information, there are plenty of details available. So one can, if you want to know more in detail about this, you can browse through the internet. And they have some good book about Egyptologist mathematics. So you can refer such books for which you can get these details here. And there is an important chamber inside the Great Pyramid called King's Chamber, which is very large actually. And if you look at this, this is a space diagonal connecting the top corner to the opposite bottom corner. This is a space diagonal, not plane diagonal, it's a space diagonal. If you look at this triangle here, this is a right triangle in the ratio 3:4:5. See, to want to make a right triangle very effectively, they used the condition that a square plus b square is equal to c square. So probably Egyptians as well as Babylonians who lived before Greek period and before Pythagoras period knew the idea of right triangles, constructing right triangles, and they probably knew that if you choose triangles in the ratio whose sides are in the ratio 3:4:5, then the angle subtended opposite to the largest side, namely 5, will be right angle. So even today, if you construct a rectangular building, the building that we construct, if you see the walls are at exactly right angles. To get the precision of a right angle, you have to choose the dimensions of the length with height ratio in the ratio of sides of a right triangle. Some right triangle that you choose. Only then you get a proper right triangle. A right angle subtended at the legs the triangle that you construct. So legs are the two shorter sides. The angle between two shorter sides should be a right angle for getting a right triangle. And Egyptians probably knew this fact, and they used it very effectively because you can see so many right triangles in their construction of Great Pyramid. The other triangle connecting the King's Chamber, the shorter rectangular portion here, will be of the ratio 2 is to root 5 is to 3. And you see the condition for getting a right triangle is a square plus b square is equal to c square. Here c is 3, so c square is 9. A is 2, b is root 5, so a square plus b square is 4 plus 5 is 9, 9 is 3 square. So this triangle satisfies that condition. In fact, you can geometrically construct root 5. Though in scale measurement you can't measure root 5 through proper scalings, but through proper ruler, you can, using ruler and compass, you can construct root 5. So root 5 is one of the constructible number. It is quite remarkable to note that Egyptians knew this fact also. So some of the irrational numbers are constructible, some are not. Okay. So now coming to Pythagoras, who lived some millennium after the construction of all the Egyptians, pyramids and all those things, he probably guessed a theorem, which is today very famously called Pythagoras theorem in his name. But there are so much speculations and so much controversies that were lying behind whether Pythagoras really invented Pythagoras theorem or discovered it, or some of his associates discovered it. That is one of the things. Even there are some speculation that he came to India and learned Pythagoras theorem from here and then spreaded the news there. And there are so much of things that huge research were going on still. But whatever it might be, we are greatly benefited from the discovery. That is what we are mainly concerned with. Okay, so if you take a rectangle, this is a beautiful visual proof of Pythagoras theorem. I will just go through. It's very simple. This is called the Chinese translation proof. So if I have a rectangle over here whose sides is of length a plus b, so this length is a and this length is b. So this is a square, in fact. So you have a square of side length a plus b. This is 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 a plus b. Okay. Now, because this is a, this is a, this area is a square. This is a, this is b. So this area is ab. And this is b. This is b. So this area is b square. And this is a, this is b, so this area is AB. This is C. So this two portions constitute of area AB. This is AB, this is A square, this is B square. Now, you get this kind of portions in a square of length A plus B, side length A plus B. Now, what I'm going to do is push this piece over here, push this here, bottom, push this to the right. Keep this green as it is. This is called translation, just pushing pieces. So if assuming that these pieces are movable, you push this piece down, so this piece will come down here, and push this piece to the right, the blue piece, you get this one here, so this will come here, and this space will be empty now, and translate this piece in. Push this piece here, red color piece to this portion, so you get a portion here. Now those four right triangle pieces were assembled in a different way. So the area of this four colored regions will be equal to area of this four colored region, which means area of the white portions will be equal to area of this white portion. So area of these two white portions should be equal to area of this white portion, because I have the same square and same pieces. No additional pieces are joined here. I'm just translating. Upon using the same pieces and moving here and then, the area will not be changed. So because of the invariance of the area, the sum of these two areas will be equal to this area. This area is a square, this area is b square, that will be equal to c square. Because the triangle has hypotenuse length c. So this is c, this is c, this is c. So the inner portion here is a square whose side length is c, therefore the area is c square. Therefore a square plus b square is c square. So one-liner proof, and wonderful proof, which is called a translation proof, probably discovered in China. So it's called Chinese translation proof. But anyway, Euclid gave the first proof of Pythagoras theorem in his Elements book, given as proposition 47 in volume 1 in the Elements book. So those who are interested, in fact, the book Elements, which is comprising of 13 volumes, is the first written book in mathematics. Just like Tolkappiyam for Tamil language, the book Elements written by Euclid is the first written book, documented book on mathematics. Among those 40 three among those 13 volumes. In the first volume, you find Pythagoras theorem proved by Euclid, not by Pythagoras. Pythagoras never gave any formal proof of this theorem. He just mentioned it. So Euclid gave formal proof of Pythagoras theorem mentioned as proposition 47 in the book. In the first volume, I think there are around 60 propositions, and among those 60, 47th proposition is Pythagoras theorem. That's also a wonderful proof. Those who are interested can look at that. Okay, so coming to the case of the next important scientist, it is Archimedes. If I want to say that you have to apply mathematics, especially to engineering, it will be very apt to introduce this great mathematician and scientist. If I do not mention it, then I will be making a big sin. Okay, so it is remarkable that Archimedes not only was a great scientist but also a very capable mathematician. He was one among the person who introduced calculus for very practical purposes. So Archimedes, in fact, historically would be the right person to credit with the discovery of calculus. Okay, not I mean, if you this findings were done very lately, of course, and you find he discovered so many scientific instruments, very simple, like pulley or lever. This is a lever, Archimedes lever, which can, and this portrait was a epitome of scientific findings. It was said in Archimedes' work that he once said to his friend that, "Give me a place to stand on earth, I will move the earth," which means that he have the power of scientific thinking to even lift up the earth by his findings of lever. He projected himself like lever can be used in such a fashion that it can even lift the earth. So that is what he wanted to say. In fact, this is actually one of the proverbs that you can take for scientific findings. So if you give us a small place to stand, we will move the whole place. So that means you can discover so many things as time progress, and you can think beyond what is done previously. And this is the discovery of Archimedes' proof, where the spiral shapes are used, and he cleverly designed the spiral shapes, which are done mathematically, of course. Okay, some mathematics is used here. I think the spirals here are named after him as Archimedes Spiral, which is one of the big things that he discovered. So if you have a water here, and if you turn down the lever here, just rotate it, the water will be pushed up from the bottom through this spiral shape, and it is poured into the container that you keep here. So this is one of the efficient of using water storage technique right from a well or a lake or something, where you can use this object. In the ancient times, they did this. And of course, he is well known to the common people for his buoyancy principle, where depending upon up thrust that is imparted into a tub of liquid of something, the mass of this object will be equal to the liquid poured into the liquid displaced into the container. So the amount of liquid displaced here will be equal to the mass of this. Okay. That is what he discovered, and there's a nice story about that which is already known to everyone, so I'm not going to that. And he also determined center of gravity for many objects, like a thin line segment. For a line segment, the center of gravity lies at its midpoint. And what is, by the way, center of gravity? Center of gravity is a point in which the whole weight of the body or mass of the body will act through. It may or may not lie on the body. For example, for a line segment or for a uniform rod like this, center of gravity lies in the object itself. In fact, for a line segment, center of gravity will be at its midpoint. For a thin uniform rod, the center of gravity will be at its midpoint. For a circular disc, the center of gravity will be at its midpoint, and this points are in the. Whereas for a uniform lamina, circular ring or lamina, portion between two circular rings, okay, just something, again the center of gravity will be at the center, and this center of gravity point will not be in the angle. So center of gravity may or may not be on the object, but the idea is the whole mass of the body, the whole weight of the body will act through at that point. So the idea of center of gravity is extremely important for engineers. to push it or through to carry the whole object. Supposing if I'm constructing a big bridge, like these days there were big over bridges are constructed for transport purposes. So for constructing such big over bridges, they do the construction somewhere else. They don't construct the bridge at venue. They construct it somewhere else, and then they carry it through trucks, big trucks, and then they just place it side by side. When they use cranes for using placing those big blocks, those blocks, as you imagine, will be of huge weight. I mean, maybe in tons or thousands of tons or something. And therefore, if something happens, if you have a good idea of where the center of gravity lies, and if you look at that center of gravity and push the object and make the object lift at that from that point, applying little force, then it will be easy for you to place the object of that mass. Whereas if you do not have any idea about center of gravity and push the object or pull the object at some other point rather than center of gravity, there is a great chance that it may slide and fall away, causing great damage not only to the structure but also to the people who are nearby, and great loss will be incurred. And therefore, the idea of center of gravity is very essential for engineers, especially for different shapes of objects that you construct with. And it was Archimedes who gave the first mathematical proof to way to demonstrate the center of gravity of triangular lamina and many other lamina like quadrilateral lamina, rectangular lamina, a solid cone, a uniform cone, and other things also. Okay. So for a non-uniform lamina like this, which has different masses at different places, center of gravity will be given by its weighted arithmetic mean. Okay. So you can look details for those who are pursuing mechanical engineering might have studied much about this, and those who are pursuing mathematics courses, BSc mathematics course, will also could have done this by integration. Like you can find center of gravity, the coordinates of the center of gravity through integration. And that formula was first given by Archimedes. Okay, now if you have a big bar here, and this is a fulcrum to balance the bar, where you place two different weights, you see the balancing point, the fulcrum point, will be close to the bigger mass. So what kind of relationship that you can have between this balancing point and the masses that were attached to the ends of the big bar, like this one? Maybe this is a uniform bar. So this mass is lesser and this mass is more. If the masses are equal, then the balancing point will be at its midpoint, because we know that the center of gravity within uniform rod will be at its midpoint. Suppose if I have two different masses, one smaller and one larger, then the center of gravity will be shifted towards, it will be near to the one which is larger mass, but how much near, where it will be the fulcrum point. And that was answered again by Archimedes. And this is called Theorem of Moments. So you listen here, this is the fulcrum point. If this is of 100 kilograms and this mass is of 60 kilograms, 100 is more than 60, the balancing point is near to the 100 kilogram, the larger mass, as I have shown here, in such a way that this product, this distance is, this end point to this balancing point is 3 units, and this distance from this balancing point to the right side point of smaller mass is 5 units. So it will always, the fulcrum point, balancing point will always be located in such a way that this product here, 100 times 3, will be equal to 60 times 5. As you can see, when you multiply 100 into and 3, you get 300, whereas if you multiply 60 and 5, you get 300. So this product should always be equal. So the balancing point will always be located in such a fashion that this product will be equal to this product. So this relationship was again designed mathematically by Archimedes. And you can see, if you have a boat here, if the center of gravity is located at the mast at this point, which is a very higher position compared to the bottom of the boat, then the boat will be unstable even for small ripples in the sea, and it will eventually fall down. Whereas if you make the center of gravity at the very lowest position below the mast here of the ship, this pole here, which at this point, then the center of gravity will balance the mass above the surface level, and therefore the stable you get the condition of stability of the boat, and therefore even for small disturbance, the boat ripples that occurs in the as the wave forms in the sea, the boat will travel smoothly. So the location, as I told you before, of center of gravity is very essential for constructing ships, for constructing objects, for lifting heavy objects and other things also. Even for sports, if you look at this here, this is the baseball bat. The center of gravity will be closer to this position. So if you hit the ball such a way that the center of the ball is in line with the center of gravity, then you almost get a home run. In the sense that it is home run is just like hitting a six in cricket match. In cricket, the maximum run that can be scored from a ball is delivered as 6 runs. And therefore, similarly, if you hit above the playing space, it is called home run. And for getting home run, if a person making the batting in the baseball hits the ball such that the center of the ball is aligned with the center of gravity exactly at this position, then it will have maximum impact on the ball, and the ball will travel more distance compared to hitting at this point or some other point. So even if you can hit here, or you can hit here, or you can hit here at some other point, but it will fall very short. You don't get home run chance. Okay. Now again, the legacy of Archimedes lies in this beautiful discovery. This was considered himself to be one of his great discoveries, and he insisted his followers to inscribe this in his tomb after his death. Okay. Now what happened is he thought of finding volume of a sphere. See, the volume of sphere, like sphere is a curved object, not like cylinder. Or see, cylinder has top and bottom, which is circle, which are plane curves, but in sphere there's no such plane curve. You don't get plane section in a sphere all around. Everywhere, if you rotate the sphere, it is completely having a curvature, whereas in cylinder it is not so. In other words, you can take a rectangular sheet in a plane and just fold it end to end, like lengthwise or breadthwise, and get a cylinder. But you can't do such thing in getting a sphere. Like exact sphere is not formed. Even if you take a circle and rotate, there will be some wiggle here and there. So sphere is a complicated object, especially in those days when calculus was not introduced. Today, finding volumes of regular as well as non-regular solids, or uniform as well as non-uniform solids, were quite easily accomplished thanks to the software and other computer gadgets that we have, the software things that we have. But in those days, it was not so. The primary idea behind locating such things is done using center of gravity by Archimedes. I just go through such discovery of Archimedes. So he thought of a cylinder such that the height of the cylinder is equal to the diameter of the sphere inscribed in it. So the sphere has radius r, this is r, height of the cylinder is equal to the diameter of the sphere, which is 2r. Now it is easy to know the calculate the volume of cone as well as volume of cylinder. In other words, volume of cylinder and volume of cone is very easily known if you know the base radius and height of those objects. In particular, we could have studied in lower classes in mensuration in 10th class in particularly, that if you have a cylinder of radius r and height h, then it will constitute into 3 equal cones. You can make 3 equal cones from that by cutting these things. You can even measure it by putting some sand or some object of those objects. So 3 cones volume will fill 1 cylinder volume when they have same radius and same height, base radius and same height. Now, knowing this formula, Archimedes, what he did was he just thought of putting this object. I do not know volume of this sphere. I want to find volume of this sphere, but what I know is I know volume of a cone and volume of a cylinder. So knowing these two, Archimedes discovered this volume by principle of balancing, or what is called principle of moments, or whatever we discussed here. Okay, so this is the idea that he used here. So you can see that the volume of one cylinder he calculated that to be equal to volume of the cone and the corresponding sphere, where sphere is inscribed in the cylinder, which means that height of the cylinder is equal to the diameter of the sphere. So volume of the cone, the left hand side, I do not know this volume. So let us assume volume of this sphere to be V. I do not know. But what I know is volume of this cone. So pi r 1 by 3 pi r square h. H is 2r, as you know. Height of the cone as well as height of the cylinder is 2r. So 1 by 3 pi r square h plus volume of the sphere, which is V, that is equal to pi r square into h. H is 2r. So this is volume of cylinder, this is volume of cone, volume of the sphere, that is what we need to find. So the h becomes 2r here, both for cone as well as cylinder. So if you compute this, this is 2 pi r cube and subtract it, you get volume of sphere. So using the basic balancing principle, Archimedes could determine the volume of sphere very efficiently. And he used the ideas of pulleys and other things to safeguard his country from the Romans, who were opponents to their country people. And those instruments were effectively done using all those little mathematical principles. And using these ideas, he could destroy the enemy ships whenever they approached their country. Like catapult and other objects were used like strings. This string will lift the with some force applied at the other end, will just lift the ship and pour it down into the sea. The whole thing was getting damaged. And one of the other important things that Archimedes did was using the ray property of parabolic mirror. So the parabolic mirror has a property that whenever sun rays hit, usually the sun rays are almost parallel. So if you have parallel rays hitting at the circumference of a parabolic mirror, they after hitting they will always converge to the focus of the parabola, and that's called the focal point. But in other case, if the rays emerging from the focus will hit anywhere at the circumference of the parabolic mirror, and they will emerge parallelly. So both ways it is true. If you have rays hitting at the circumference of the parabolic mirror, they will always converge at the focus point. So this is called parallel convergence property of the parabola, okay? Or reflection property, parallel reflection property of the parabola. So what Archimedes knew of this geometrical fact, and he used this fact effectively to observe what is called Archimedes heat ray. So he placed the mirrors in such a fashion that the rays from the sun hit the parabolic mirror, and then they are reflected to the ship that is approaching to their country. So this is the enemy ship that is approaching Archimedes' country. Archimedes lived in a place near Italy called Syracuse. So whenever Romanians approach Syracuse country, that island, Archimedes used to use these devices that he discovered very effectively and destroy the enemy ships. And one of the ways that he did was using this parabolic mirror property. So when the sun rays were hitting the parabolic mirror, they all get reflected using this focal property. Okay, all the rays here, which are parallel from the sun, will hit the parabolic mirror and they converge to the focus point. This point is the focus. So he will place in such a way that at any point of time, the rays are converging to hit the enemy ship at some point. When the ship approaches a certain position, it will always be hit by that rays, and therefore the heat generated by the sun rays rather. So the sun rays are extremely hot, and if they converge from so many mirrors, it is said that Archimedes used more than 1,000 mirrors, not just 5 or 10 like this. He placed more than 1,000 mirrors like this, and the heat generated is enormous, so that the whole ship get burned after some time. So this is one of the practical thing. People, scientists and engineers were speculating this, whether Archimedes did this or is it a myth. Some people from Australia and some people from UK joined together, and they wanted to simulate this property. So they placed some 500 mirrors or so at the coastal area, and then they put a ship which is done for this purpose, this experimental purpose, some ordinary ship made in wood. And when the ship approached at certain positions, not at all positions, but when they observed that when the ship approached certain positions, though the ship was not burned as the the story said, certainly it caused damage, huge damage to the ship, and no one in the ship, probably someone could have stayed in the ship, could have not survived because there was so much of heat generated in the ship surface. So probably generating more heat is what Archimedes thought of, and he put into this effect very effectively. So people and today probably believe what Archimedes could have done is probably true, though to the extent not as justified as the story says, the whole ship getting burned. The whole ship may not get burned, but the people in the enemy ship may get distracted, and they do not withstand the heat ray that is reflected from the mirror, so they could have turned back to their own country. They will not approach anymore. That could be the probable reason. So recognizing Archimedes' genius and his remarkable scientific discoveries using the basic principle of physics and mathematics, his portrait was engraved in the medal called Fields Medal. This is one part of the Fields Medal. A gold coin engravement of portraying the engravement of this Archimedes head was given to Fields medalist. Incidentally, there is no Nobel Prize offered for the field of mathematics, the discipline of mathematics. So the greatest recognition that a working mathematician can get as of today was the Fields medal. And in one portion of, any coin has two faces. So one such face of the gold coin that was given to the Fields medalist contained the face of Archimedes like this, with this description. Okay. I do not unfortunately remember the translation behind this description, but it is regarding what Archimedes said. Okay. So that is the honor that mathematicians give to the great man who lived in those period. In fact, as the story goes, he was drawing circles in the sand, and one Romanian soldier came and cut off his head during the time when he was working in a geometry problem. The last word said by Archimedes during that time, before he just was killed, was, "Don't disturb my circles." So that is what he said, and his head was thrown away by this one. So this is so he devoted himself completely into making great discoveries. So Archimedes was probably the first scientist, the first engineer to put into scientific principles into many engineering discoveries. So any engineer should know more about Archimedes. I would probably request all engineering students from any branch for that matter to know more about Archimedes and his remarkable achievements. Okay? More scientifically, not through stories. Read about his discoveries scientifically. Okay. Now this is how mathematicians see about the waves. I see waves as the interference of this sine. This is sine curve. As you can see, this yellow curve here is a sine curve. I have translated the sine curve by 2 units here and by pi units here. Okay. So if you translate the curves, you see this wave pattern emerging. Okay. And if you make difference in the amplitude, you see smaller waves and larger waves, one meeting the other at different points of time. And this interval between successive waves is called a period of the wave or something. And there's a huge topic devoted to the study of wave patterns that is called wavelets. It's a huge research area, and a lot of research is going in the study of wavelets. This is study of propagation of waves. See, when you talk about waves, you talk about sea waves, sound waves, air goes in a wave, light sometimes goes in waves. And so almost all physical objects that were transmitted from one place to other place were moving along waves. Okay, so this is what even astrophysicists claim, that particles in the universe move through waves, and the string theory is developed in that aspect. So you see, a lot of things were depending upon the propagation of waves, and therefore mathematicians did great study right from 3 or 4 centuries ago to present time in the study of waves, and made some beautiful discoveries which were helping engineers to formulate new theories and simulate the patterns observed in the nature. Okay, I will come across few such things, but don't worry, I'm not going to do any problems here as what you do in the class. So I'm a person who always think that producing things visually makes more effective. learning rather than doing problems or working out with already committed formulas in our mind. So that is only for exam purpose, and for going to next stage, that is required for our curriculum. But knowing things scientifically and becoming a good scientist is something very different from what we do in our class. So in other words, to do actual research is completely different. That experience is completely different from what you experience in your usual learning, whether it be in school or in college or in any other mode. So the research experience is a wonderful thing, and if you come across in future to research experience, you can know what I'm saying. Okay, so I'm going to present the ideas only through visuals, so you can sit and enjoy. So if I take f of t is 1, and you know that you could have studied through formula that L of 1 is 1 by s, isn't it? See, L of f of t, for the sake of formula, is integral t0 to infinity e power minus st f of t dt. So in that, if you substitute f of t is 1 and integrate e power minus st from 0 to infinity, you get 1 by s. Okay? So this is the graph of 1 by. So this is the input, this is the output. So if you consider this as a, see, the word transform, you study so many transforms in your syllabus, like Laplace transform, Fourier transform, Z transform, Hilbert transform, orthogonal transform, Gabor transform. So many transforms are existing, whatever that you might have studied already, or you're going to study in future, or even in research you study about Gabor transform, binomial transform, and other things that you usually use in different areas of science that you are doing, pursuing the research. But all these transforms have specific advantage and specific uses. So depending upon the situation that you are doing your research, you can use that particular transform to arrive at your desired result. Each has its specific advantages and specific need of usage. So in other words, all these transforms were tools, just like different size of spanners that a mechanic uses. So if the screw is bigger, you use big spanner. If it's smaller, to unscrew, you use smaller spanner. So similarly, this transforms are just like tools for a mechanic. You are the mechanic that you want to deal with, and that is why the precise reason why you are taught all these concepts in your curriculum. Because in one day, if you go to the company and if you are given a real-time project to design something, you need all these tools. You can't say then I will go to the school again, or I do go to the college again and learn from a teacher and come back. That is not possible. So whatever you learn now, if you have learned it properly, you can use those ideas very effectively in future. As a production engineer or a mechanical engineer or a computer engineer doing some big algorithms, like people are doing data science now, and even for marine engineering, you need a lot of mathematics. I will, if time permits, I will just highlight some of those things. So there is some disturbance in the. Please make it silent. So if the input signal is 1, the output signal is a curve, and this curve is a part of a rectangular hyperbola. See, this is a rectangular hyperbola. One branch of that. Okay. And if the input signal is exponential curve like this, the output signal is this. And you could have studied in your class that Laplace transform of e power at is 1 by s minus a. So a is 1 here. And I mean, unfortunately, I could not ask questions to you because we are not facing face to face, and therefore there is no problem, possibility for me to ask questions to you. But one thing that you can see is, if you can observe a common pattern in output signals here. So if you see this output signal here, the output pattern, you see output pattern here. Though the input pattern is completely different, the way that output pattern goes is somewhat similar for any input pattern that you take here. For any input pattern, the Laplace transform, the output pattern behaves a little bit similar. In fact, you can see that the output pattern goes to 0 whenever s is very large. This is f of s. The answer is it's a function of s. So the f of s touches x-axis. It is very close to x-axis. It means f of s approaches to 0 whenever s is very large. As you can see. In fact, this is one of the important condition for Laplace transform. If L of f of t is f of s, then limit s tends to infinity, f of s becomes 0. That is one of the requirements, which means that whatever input signal that you give, after a long time, the output signal will go to 0. So this is one of the chief characteristics of Laplace transform, which you find in other transforms also. So if you take Laplace transform of sin t, sin a t is a by s square plus a square, where a is 1. So this is 1 by s square plus 1 because a is 1 here. This is output pattern. As you can see, for larger point of values of s, f of s goes to 0. So this is the graph of 1 by s square plus 1. Initially it is large, but as s becomes larger and larger, it drops down to 0. Again proving the fact that limit s tends to infinity of f of s is 0. And now if you take this graph, this is s into f of s, this green portion here, this is f of s, and this is, I'm multiplying that by s. So this is the Laplace transform value. If you multiply this by s, you get s by s square plus 1. And if you look at this s by s square plus 1 graph as s is large, that is 0, and that value 0 is equal to the function's value at the point 0. So limit of sin t as t tends to 0, sin 0. Sin 0 is 0. As you can see, the curve passes through origin. So this is 0. The left hand side is 0. The right hand side is also 0 because this is a green curve, s by s square plus 1. Whenever s is large, it approaches to 0. So both are 0 here. This is the what is called the initial value theorem that you learn. Limit t tends to 0 of f of t. Limit s tends to infinity of s into f of s. So this is the graphical description or derivation of, or verification rather, of the initial value theorem for Laplace transform. So if you take cos t, this is the graph of cos t, the input signal. The output signal increases and it drops down to 0, as always the case. This is f of s for me. In this case, if you want to verify the initial value theorem, limit t tends to 0 of f of t, cos 0 is 1 here. You see 0 comma 1. So this left hand side is 1. What about the right hand side? If I multiply this by s, you get s square by s square plus 1. And this, as s is very large. So if, for example, if s is 18.924, the answer is 0.997. If s is 25 point something, the answer is 0.998. If s is 31.461, s is 0.999. So as you can see, whenever s is very large, this s into f of s, which is s square by s square plus 1, approaches to 1. So this is 1, this is also 1. You get this line, this graph of s into f of s, namely s square by s square plus 1, is almost 1, which is equal to the cost value at the point t is equal to 0. That is 1. So both sides are 1. Again, this is a geometric verification of the initial value theorem of Laplace transform. Now let me tell you this point also. L of t square, this is Laplace transform for other functions. This is 2 by s cube. This is L of and again this is verification of initial value theorem for L of t square, as you can see. So at the point t is 0, this is 0, t square is 0, s into f of s is also 0. So this is another picture. And coming to Fourier series, if you study about Fourier series, the idea of Fourier series is so beautiful because it was initiated by French mathematician Joseph Fourier. The Fourier series is just like adding numbers or adding some objects. Now, like if you add 1, 3 and 5, you get 9. So if you add some set of numbers, just like adding numbers, if you can also add wave. This is what Fourier observed. To get a general wave pattern, it is enough to add few nice wave patterns. This is a nice wave in the sense you can write the equations of this wave, you can write the equations of this wave. This is exactly half the phase of this. Then this is this is exactly half the phase of this, and this is 1/3 of the wave of this. So if for example, if this is sin x, this is sin 2x, this is sin 3x. If you add the sin x and sin 2x and sin 3x, you get this general wiggly pattern, this general wave pattern. So what Fourier said was, if this is your f of x, a general wave pattern, namely f of x, can be decomposed as sum of very nice wave patterns. So this is a1 cos x, this is a2 cos 2x, this is a3 cos 3x, and a4 cos 4x. So this is just an example to show how a general wave pattern, namely f of x, can be written as sum of very nice wave patterns. like amplitude 1, this is first harmonic, this is second harmonic, this is third harmonic, and so on and so forth. So if you add this harmonics, you get a general wave pattern. This is what Fourier series is all about. So when you are given a general function like f of x like this, if you add harmonics to each other, like first harmonic, second harmonic, and third harmonic, they give this wiggly pattern. You often observe these wiggly patterns in seismograph readings, in our heartbeat reading, like when you take cardiogram, ECG, electrocardiogram reading, the heartbeat readings will portray this way. So in those cases, Fourier series and Fourier transforms are effectively used in ECG, in medical instruments like ECG and other things. In fact, heavy duty mathematics is used in CT scan instrument. I'm not going to do that now. Okay, in CT scan and other MRI scans, you use other types of branches of mathematics, not Fourier series. Fourier series and Fourier transform are also used to extract the image from 3-dimensional to 2-dimensional, projection image. So all these ideas were used very effectively in today's scenario. So this is the, I mean, you could have done this in your class by using formulas, but I'm showing through pictures. This is the graph of x square in the interval from minus pi to pi. The Fourier series of x square will looks like this. This is only 3 harmonics. I'm adding only 3 harmonics. Bn is 0 for x square because x square is even function, so you don't get sine terms here. You get only, this is up to 6 harmonics because you get cos 6x. So up to 6 harmonics, you see this graph resembles almost this graph, though not exactly, but the graph, this is the right hand side of the Fourier series, this is the left hand side, which is what we have taken. So if you add more and more terms here, more and more harmonics, this will exactly look like this. This is what Fourier said. So this is the graph of x, the wave pattern, okay, of x, and you see the similar things, but upon adding up to 6 harmonics, this is not good approximation to this. This won't look as good as this one. Okay, so if you compare these two, this is quite different, which means that you need to add more number of harmonics to get this one. And x is a odd function, therefore you get only sine term. Only bn will exist. There's no a. For odd function, only bn's will exist. That is why you get only odd harmonic terms here. And this is a mixed function. You could have done this. So you see this same pattern here, but again, all this bigliness will not be observed. Few things. So here there is a bend here. Those bends are observed here also, but not exactly. So which means if I want to replicate the same pattern here, I should not stop at this place. I should keep on trying to add as many possible things. I have added only up to A3 and B3 here. So only 6 or 7 harmonics were added here. So you need to add little bit more to get this pattern. So this is what you can know about studying about Fourier series. As I told you, the idea of Fourier series and Fourier transforms were effectively used in so many branches, especially in image processing, in medical scanning and other things. Okay. So Fourier series approximation of a square wave. This is a square wave pattern. This is a square graph. The first approximation is this. This is the second approximation. So as you increase more harmonics or more terms in the right hand side, when you compute a and b n for larger values of n and put together, add them together for more number of terms, you get this term exactly resembling the given term. So for the first few terms, there's a big difference between the actual pattern and the observed pattern. But here, if you add up to 49 terms, up to 49 harmonics, it looks similar. But interestingly, there is a French mathematician, I do not unfortunately remember his name now, very recently, some years back, he proved that it doesn't matter how many harmonics you add the right hand side, the observed graph will never exactly fit the given graph. There will always be some gap here and there. So there is, you can't exactly fit the right hand side, will not exactly always add up to the left hand side. It will resemble it and it will fit almost as good as possible, but it will not fit exactly. This is what that mathematician proved. It was a very interesting proof actually, which was quite surprise to the mathematicians and engineers also. Okay. But they thought it would exactly fit. This is the approximation for triangular wave. And you see this is for parabola x square. First approximation is like this. Second approximation, as you can see, is much better than the first approximation. Third approximation is better. But if you go to 6 approximations, up to this portion, you see the Fourier series exactly fits up to this interval from say -3 to +3. The observed pattern exactly fits the given pattern x square. And this is Fourier transform. The idea of Fourier transform again is used in signals and systems in EC. Those who study electronics and communication engineering use Fourier transforms. See, the word transform means in Tamil it is urumatam, then changing its structure. So whenever I give some object in input, the structure of this object completely changes in the output. As you can see here, the structure here in the output completely drastically changes from the input. This is a straight line. Input is a straight line. The output is a very bigly curve. And as observed in the output property of Laplace transform, this signal here, output signal, drops down to 0. It approaches to 0. So for the most of the transforms, it is so. Because for a long period of time, the output signal should go to 0. That is one of the expectations that we come across in transforms. So you see, for this input signal, the output starts here and it goes up and come down, goes up, come down. But the height of that oscillation is getting smaller and smaller. Eventually, it drops down to 0. So this is Fourier transform of x. F of x is equal to x, and this is Fourier transform of x square. See, again the same pattern. As the time grows, the signal drops down, the output pattern drops down to 0, but the bigliness is more for x square compared to x, which means there are more number of oscillations for this input pattern compared to this input pattern. So you can study something about this. For example, if the seismograph reading goes like this, then there is a square pattern shock that has been observed in the tectonic plates compared to the linear pattern. So if the output reading in the seismograph readings comes like this, then the scientists can guess that the actual force that is exerted between the tectonic plates is of second degree, because this is x square. That leads to this pattern. So this is the output observed in the seismograph reading. Okay, seismograph is an instrument recorded, which is used for recording the aberrations caused by earthquakes. Okay. Now, this is wave equation. So as you study wave equation, you have a vibrating string here. If there is nothing that I can do, there is no vibration. This is the wave equation where I taken the c square or a square, whatever we call as 1, that is 1. And if I plug this string near to the midpoint, approximately, not exactly done, of course. I'm very poor at this creation of drawing and all those things. If you assume that this point is the midpoint of the string and plug it, this is the wave pattern that you get. This is the vibration that is caused. Of course, I used some software to generate all this output pattern for all the pictures that I have shown. It took quite a bit of time for me to generate all these patterns here. There are nice softwares that can be used. So if you plug the midpoint of the string, you get this kind of output. So the vibrations you see, and the same pattern is replicated above as well as below. So this is above, and after some time the vibrations goes below. So which means this is the maximum value and this is the minimum value. So it oscillates both ways, which is the string oscillates above as well as it comes down below. Only then you get a wave pattern. So that wave pattern is assembled here. This is above, and after some time it goes below. After some time it goes above like this. The vibration changes its pattern from above to below. And if I plug the string at 1/3 and 2/3 portion, in fact you do this as a problem in wave equation. If you plug a string at 1/3 of the whole length and 2/3 of the whole length, then the vibration will look like this. So this portion of vibration, the string resembles this part, and this portion resembles this part. You can see the similarity. So this is almost a triangular shape. You get a triangular shape here, but this is not triangle. This is a curved path here, and you get a curved path here. Same kind of path is replicated here, but along with some vibrations, not straight line, but with some vibrations. And after some time, interestingly, this part comes above and this part goes down, which means the vibrations reverse its aspect. So whatever comes down is getting reversed after some time. and it keeps on repeating because it's a periodic motion. So this is how the vibration. So knowing this kind of vibration, if I know that the vibration of string is like this, I could have probably guessed. I could probably guess that the original string is of this type. And conversely, if the string is of this type, I know I have mathematical methods to generate this kind of vibrations. So this is where vibration strings, you need to study those properties and formulas involved in vibration of strings. And to find this part, you need Fourier transform. Okay? You need half-range Fourier series expansion. And this is about the heat equation. I will stop as soon as possible. This is about the heat equation. Ut is uxx. So this is the parabola x square, the input path in brown color. And if you use this up to 10 seconds, I have done here. This is the seconds. Okay. So assuming that initially the heat transformed is of quadratic nature, that is x square. At the point 0 it is 0, at the point 2 it is 4, at the point 4 it is 16, at the point 10 it is 100. So 100 degrees. After say 10 minutes, maybe in minutes, after 10 minutes, the object gets heated up to 10 degrees. And if you use heat equation, the solution has heat propagation. Heat propagated in the object in this pattern will be of this form. And as you can see again, as I told you, for larger point of time, because we assume in all governing this boundary conditions of all this heat equation and wave equation problem is that there are no vibrations or oscillations or heat propagation at the end points. In other words, though the string gets vibrated at all points, there is no vibration at left end point as well as right end point. The end points have no vibration. Only the points in between the end points are getting vibrated. Similarly, there is no heat propagation at the end point, namely at the point 0 and 10. I am taking the interval from 0 to 10. So you can observe the heat propagation pattern between 0 to 10. Because of that reason, what you call mathematically as u of 0 comma t is 0, u of 10 comma t is 0. So the ends are isolated. You could have done this kind of problem in your class. If the ends are isolated, there is no heat propagation at the end points. Similarly, the end points have no vibration. Okay, so that you discuss this as one of the boundary condition in solving wave equations. As u of 0 comma t is 0, u of L comma t is 0, which means there is no vibration at the left side as well as there is no vibration at the right side. So this is the quadratic pattern, and you see the heat propagation initially dips here and then increase and then dips somewhat and then increase, then dips, then increase, then dips, then increase, and finally after reaching this maximum value of 100 degrees, so at this point of time, because I have insulated endpoints, the heat suddenly drops down and it drops down to 0 between short period of time. Okay? And it is quite interesting. You can use maxima, minima to find at which point, at which time interval, at which time occasion this attains its maximum value and minimum value and all those things. Okay, so this is what. So if I need to know, say for example, at what point of time the heat propagation is attained 60 degrees, I can plug those values in the equation, the solution that I have obtained here. So you drop a vertical line here. So this is the time interval, which is approximately very close to between 6 and 8 here. And if I want to know at what point of time the heat propagation is nearly 40 degrees, I can drop a vertical line here that is very close to 6. So this kind of heat propagation gives you somewhat a good idea about at what time you get what amount of temperature that you require in the heat propagation problem. So solution helps quite a lot in understanding the phenomenon. Yeah. And this is the initial pattern is a parabolic with the downwards parabola, because it's 2x minus x square. The coefficient of x square is a negative term, so it's upside down parabola, open downwards. Okay, so the heat propagation starts here, and you can see at the point when x is 0, you get 0 here, 0. So it starts oscillating. It drops down to minimum oscillation here. Because the ends should be at 0, you get 0. So when you are going to use this form of temperature, in the heat propagation problem you get only negative temperatures, not positive temperatures like this one here. You get positive temperatures here. So the whether you in the heat propagation phenomena, whether you are ending up with a positive temperature, negative temperature, depends on the initial function that I choose. In particular, if I choose a function like this, you get a positive temperature phenomena. Whereas if I choose a function like this, you get a negative temperature phenomena. This is the minimum temperature, where if you want to know the time, you can just drop a perpendicular here from this, draw a vertical from this point. So this is a time interval where you get minimum approximate. And for a constant temperature, so if I have keep my temperature to be 1 always, initially it is at 0, it will increase to some particular temperature, then starts dipping down, then starts, because the final temperature should be 0 degrees. So you get a nice symmetrical distribution of temperature pattern. Sometimes it increases, sometimes it cools, sometimes it increases, sometimes it cools, so oscillating, and then it drops. So you get a very nice pattern here, the symmetric pattern, because I have chosen a constant temperature here. So this is again, you see the common property that u of 0 comma t is 0. The temperature at the endpoints is always 0, whatever function that you choose here. Okay? So depending upon that, you get this. And the idea of complex functions is used to generate beautiful surfaces from which you can study so many things. Like these are all beautiful diagrams looking like chips. This is the real imaginary parts of square root of z, result is x plus iy. Okay, and this is for 1 by z, real part of 1 by z, imaginary part of 1 by z. This is the graph of x by x square plus y square. This is minus y by x square plus y square. And this is the graph that you get for log z, ln z or something. You get a nice cone shaped curve, not exactly a cone, it's somewhat similar to cone, but not exactly a cone. What we call this kind of instrument that is used in functions. And Tamil Nadaswaram, just like playing instrument. And you get this kind of wonderful spiral pattern here, which represents imaginary part of ln z, spiral pattern. Now, what kind of, apart from pleasing structures that I get, what kind of practical use that I get? See, if you want to take an image like a photograph of any person and you want to enlarge it, you can use complex valued functions, put the inputs accordingly and create some suitable function accordingly, and you can rotate it, or you can enlarge it, you can shrink it without losing much information from the picture. So that is where the properties are used. And I will give one more application before I stop this lecture by presenting the ideas of what is called the importance of study of what is called this complex valued functions, called precisely called analytic functions. Like if f of z is equal to u plus iv is analytic, if it is known to be analytic, then it is known fact that the real imaginary parts, namely u and v, are harmonic. In a sense, they satisfy Laplace equation given by uxx plus uyy is equal to 0, as well as bxx plus byy is equal to 0. Now, if you know that the function is a harmonic function, then the curves representing u and v will meet each other orthogonally. So this is one of the very beautiful property that you find among the existing properties of analytic function. So if you take, for example, this is the part of 1 by z square. If you take real part of z square, it is x square minus y square. So the blue curves are x square minus y square is equal to constant. You can vary this constant and get this curves. And the red curves here are the representing the imaginary part, namely xy c square. So if you alter c square, you can get this red portion curve. And if you see the blue part and red curves, the imaginary part and real parts, namely u and v, merge, they intersect at each point at several occasions. But any of those points, if you look at, they meet orthogonally. That is, if you draw a tangent to the blue portion and the red portion here, the tangents drawn will be perpendicular. And this kind of orthogonal property is very effectively used in fluid dynamics, especially when ships are moving in dense sea. This kind of to generate some properties in fluid mechanics, in fluid mechanics, these concepts are very effectively used. I will show the next slide regarding that. And this is the same picture. The blue portion represents real part of Z cube, and the red portions represent real part, imaginary part of Z cube. As I told you, for any intersection point here between the real and imaginary parts, if you draw tangents at blue portion and red portion, they will be perpendicular at any point. You see, and you see very nice structure, like art structure here, which you can use for designs in your mirror designs or bedsheet designs or something. So the complex functions not only give scientific application, but they are very rich in art and architecture also. So you see, this is the real and imaginary parts of Z plus 1 by Z. And Z is equal to 0, this function has a pole of order 1, and therefore those points are not included in the graph. You see, whether those points function is not analytic at Z is equal to 0, so you get a gap over there. So this is real part of Z plus 1 by Z, this is imaginary part of Z plus 1 by Z, this is U, this is V, and they intersect each other like this. And again, as I told you, if you take tangents at red part and the intersection point of real imaginary parts, they cut off of them. It's kind of beautiful pattern that you find. And this real part portions, namely the blue part, is in fluid mechanics called equipotential, and the red path that you find as imaginary parts are streamlined. So in a fluid motion, there is a big idea connected with analytic function. If you know that the function is analytic, then you can say that the fluid flow is ideal fluid flow if the parts of the fluid flow are arising from as real imaginary parts of analytic function like this, whatever I have shown here. In other words, the real parts are equipotential and the imaginary parts are streamlines. You can generate the orthogonal property of streamlines and equipotentials from the real and imaginary parts of the corresponding analytic function. So there's a beautiful connection between analytic function and the parts constituting an ideal fluid flow, which is equipotential and streamlines. And see, if I try to talk about applications of transforms and other ideas, and even this portion, it consumes so much of time. But what I have shown is just a gist of probably very quick survey of what is done and what you can understand, but no equations are involved, only pictures are involved. I have done this through softwares that I have used, so probably this might help you in understanding your thing rather than doing things mechanically. At this point of time, I think it's time for me to stop the lecture. If you have any doubts, I'll be happy to answer your questions. Thank you.
Hello, participant. Any doubt you can ask freely. Sir, ready to answer for your questions. The chat box, no questions are there. It is a general question. Anyone can ask any questions.
Oh, okay. There are no questions, you can proceed.
Anyone have any questions? Cadets or non-DG student also, BBA student, it is a general question. You can post your questions directly to the resource person. Anybody from mechanical engineering? Sir, I think no question, sir. Hello. Agataji, madam.
I'm audible?
Yes, sir, audible, ma'am.
Okay, sir. Sir, can you deliver the vote of thanks?
HOD, sir. HOD, sir. HOD, sir. Hello, sir, Rajendran, sir. I think sir is not done, ma'am. Okay, ma'am. If no questions, we will go for the next session. It's vote of thanks. I request Our senior faculty member, Ms. Megapraj, will deliver the vote of thanks.
Thank you, sir. Good morning to all. First and foremost, I would like to thank our Honorable Vice Chancellor, Colonel Dr. G. Tiruvasagam, sir, and the most respected Registrar, Dr. M. J. Prakashwal, sir, for permitting and encouraging us to organize such lectures in this pandemic situation also. A special thanks to our resource person, Dr. R. Sivaraman, sir, Associate Professor, DG Vaishnava College, Arumbakam, Chennai, who readily accepted our request and headed the session in an interesting manner. Thank you, sir. Also, I thank our head of the department, Mathematics, Dr. L. Rajendran, sir, and other head and deans of various departments, my dear faculty members and students for their active participations. Once again, thanks to our resource person, Dr. R. Sivaraman, sir. Sir has explained the application of mathematics in a simple and easiest way. I hope that your knowledge would have reached all the students. Once again, I thank our chief guest, Dr. R. Sivaraman, sir. Thank you, one and all.
Thank you, sir. Sir. Sir, thank you, sir. Participant, you can fill your feedback link. Kindly fill the feedback link. Feedback is posted in the chat box. All of you kindly fill the feedback link. Participant, kindly fill the feedback link